Hello everyone, welcome for this lecture. Today we are going to see the uh, characteristics of DC motors. Okay, before going to study the various characteristics of the motor, let us revise once. So, what are the torque and speed equations? Okay, remember one thing that we are going to discuss the characteristics of DC motors only of DC shunt motor and DC series motor. Okay, let's see the formulas for the each. Okay, as we have seen, the uh, torque of the motor is 0.159 phi Ia pz by A. Okay, since this 0.5159 and P into Z by A is a constant for a given motor. Okay, therefore what we can say is this: if this term is a constant, then this torque is proportional to phi into Ia. Okay, phi into Ia, right? So, and a phi is the flux produced by the field winding. Okay, therefore the and it is proportional to the current passing through the field winding. Okay, therefore what we can say is phi is directly proportional to I field, right? So then remember these formulas, right? For a DC shunt motor, as we say, flux is a constant. Okay, means a flux constant motor also we can call this, right? So ISH is a constant as long as the supply voltage is constant. Okay, therefore this is also called as flux, means flux is also called constant. Therefore it is, this machine is also called as flux constant DC shunt motor. Okay, therefore what we can say is flux will be constant, therefore your T will be proportional to I field, means armature current. Okay, these all formulas you supposed to remember. This is general formula, this is also a general formula. Based on this, for a DC shunt motor, T will be proportional to Ia, torque will be proportional to Ia. And how about this series motor? It will be like, T proportional to Ia into phi. So where flux is not constant here. Okay, it is proportional to the armature current. Okay, so in DC series motor, therefore, so if you substitute in 5 place Ia, then T will be proportional to Ia square. Okay, you're supposed to remember these formulas, right? And we'll see how the relations of speed. Consider EB, back EMF, that is 5 ZNP by 60A. In this Z, number of conductors per path, parallel paths, and the number of poles, and this is a constant term. Okay, and then what we can say, when you say this term as a constant, then EB is proportional to phi into, so your phi into, see, this EB is proportional to phi into N. Okay, flux and speed, right? Then what we can say, we require a speed formula. So N, we can say N is proportional to EB into phi. Okay, so then this is the one formula we have got, relation we have got. Now we will see what is a back EMF for the shunt motor. These are all general formulas. Okay, so now we'll be very specific about shunt motor and series motor. Okay, let's see what is the EB for a shunt motor. It will be V minus Ia Ra. Okay, as we said, EB is proportional to phi into N. And one more thing is in a shunt motor, phi is constant. Therefore if this is also constant for shunt motor, EB is proportional to N then, right? So when you say EB is proportional to N, EB, now what we can say is EB is proportional to V minus IRA. Then in place of EB we can substitute N, because since these two are directly proportional. So N is proportional to V minus IRA. This is for DC shunt motor. Okay, remember all this, right? And then what about for a series motor? In series motor, phi is proportional to Ia. Okay, then what happens here? N is, so what is the EB formula? Back EMF formula is what? Which is equal to, so for a DC series motor, it will be back EMF is equal to V minus Ia Ra minus Ia RAC. This we have seen the formula for EB. Okay, but so here you observe. Okay, this is the EB, numerator is EB formula, right? As we know, compare with this, N is proportional to EB by phi. In a shunt motor it was phi was constant, so you directly took EB is proportional to N. Okay, that's what we have written here. You replaced EB by N. Now but N is proportional to EB by phi. Okay, in series motor phi is not constant, phi is proportional to IA, therefore EB formula you have to write divided by IA you have to write. Okay, these are all the formulas you're supposed to remember, and then these are very useful for your DC motor characteristics. Okay, let's see DC motor characteristics. Okay, so to perform of a DC motor under various condition, right, this can be judged by following characteristics. Okay, so there are few more, three main characteristics. Okay, let's see one by one. First one is torque armature current characteristics. Okay, this is mentioned as T versus IA. Okay, so torque versus armature current characteristics. Okay, this is also called as electrical characteristics. Okay, so what we can say is, to decide this characteristics of a motor, we have to draw the graph of torque versus IA. Okay, when you get a graph, in that graph it has to be represented like, graph showing the relationship between the torque and armature current is called the torque armature current characteristics. Okay, or also you can say torque load characteristics, and therefore it is, means it is also called as electrical characteristics. Okay, and the second characteristic is based on speed armature current characteristics, means we have to plot the graph of speed and IA. Okay, speed versus armature current. Okay, so then depend upon this we have to explain that graph. If you explain, that is your characteristics of DC motor of speed versus armature current. Okay, last one is speed torque characteristics. Okay, this is the again a graph which gives the relation between the speed and torque of a DC motor. Okay, that is called as speed torque characteristics of the motor. Okay, remember this also called as, these characteristics are also called as mechanical characteristics. Okay, so as we have said, we need to study the characteristics of DC motors. Here we have three types mainly. Okay, DC shunt motor, DC series motor, and DC compound motors. In that, long and short shunt DC motors, even differential, cumulative we have. So among that we are going to study only these two characteristics. Okay, characteristics of DC shunt motor and series motor. Let's see one by one. Let's take a first one. For each, okay, for each machine, all three characteristics. First one is T versus IA. Okay, that is the torque versus, means torque armature current characteristics. Speed, that is N, speed armature current characteristics, and then last one is your torque armature current characteristics, sorry, speed and torque characteristics. Okay, these three we have to study for each DC motors. Let's take first one. This is regarding DC shunt motor. Okay, so now you recall the formulas for for this DC shunt motor, for torque, okay, and for speed. Okay, these two you have to remember. Okay, so let's see this torque of and armature current characteristics. In this what happens is, for a constant value of RSH, okay, for constant value of RSH and voltage V, ISH is also constant. Okay, so therefore what you can say is TI is proportional to IA. We have already discussed, right? TI is proportional to IA. Then what should happen when current, means what happens here when loading, when you increase the loading, IA start increasing. Okay, so when loading, IA start increasing. So when IA start increases, torque also start linearly increasing, right? That is what it is shown here. First one is a torque of armature, and second one is torque of shunt field. Okay, remember here what happens. So at the beginning, okay, when you say at an on no load, okay, when on no load condition is there, then THH will not be there. Okay, but your TA will be present. You remember that. Okay, so your TA will be present, right? So difference of this one is called as your loss torque. Okay, then this is first, as we said, characteristics of DC shunt motor, torque and armature current characteristics is what? As you know, the relationship between these two for a DC shunt motor, TA is proportional to IA. If the load increases, then load current or armature current also start increasing. When this is increasing linearly, your TA is also increases. Therefore, if a current start increasing, your T also starts increases. Okay, torque also start increases, right? So this is about first characteristics. Let's see the second characteristic, that is the speed armature current characteristics. Okay, as you know, speed and armature current. So let's see what is the speed formula for this. It is nothing but speed is proportional to V minus IA RA. Okay, V minus IA RA. Okay, so what happens here is this should be V minus. Okay, V minus IA RA. Here, when the as the load increases, as we have discussed earlier, as the load increases, what happens? This IA start increasing. When IA start increases, okay, when IA start increases, right, voltage drop across this is start increasing. Then what about V minus this drop is start reducing. Okay, and then what about speed? Speed is directly proportional for this combination, so speed is also start decreasing. Okay, but okay, this is the condition what should happen. But what happens here is RA is very small. Okay, RA is a very small. Whatever change in current happens, that is going means this multiplication you are going to take. Multiplication of these two you are going to take. That is your voltage drop, right? So when you are going to take a multiplication of these two, since IA is small and RA is small and IA is larger, any whatever it may be the IA, but when you multiply with a small quantity, your voltage drop is also reduces. Okay, when voltage drop of IA RA reduces, then what about this? N is proportional to V minus IA RA, right? IA RA. So when this reduces, V minus small amount changes what? N is proportional to V. Correct? When you say this is reducing very small, means a small quantity, so then what happens here is the magnitude of this when it is reduces, so change in this will be less. So then speed is also like speed remains same, like N is proportional to V, we can say. Okay, this value is a small one, small quantity. Therefore what we can say is, so whenever your even though current changes, your speed remains remains same. Okay, a slight change will be there because of that V minus IA RA. Okay, a small change will be there, so it should be like this. Okay, it should be with this line, but it will not be there because of this IA RA. It is going to be slightly change, reduces. Okay, so this is speed armature current characteristics of DC shunt motor. Okay, and then next we'll see the speed torque characteristics of DC shunt motor. So you just, this is the combination of both first one and the second one. See what happens here is, first one what we said, TA is proportional to IA, correct? And then in the second case what happens, N is proportional to your V. Okay, means it is proportional to the N is inverse, means N is proportional to V. Alright, what happens here is, so this remains almost all, means now what we can say is speed torque, this also same. Okay, torque proportional to N, means how it is there in the first one, it is remains same for the torque. Therefore even though torque increases, okay, even though torque increases, a slight change in the speed takes place, not gradually, means not like speed means highly or very reduced. It is a very small change in speed takes place. Okay, and then we'll move to DC series motor. You just observe the formulas of DC series motor. So here for torque armature current, so torque is proportional to IA square. Okay, IA square from the formula. that is TA is proportional to phi into IA. In the series motor, IA current is means flux is proportional to IA, therefore it will be IA square. So what we can say is when the load increases, okay, when the load increases, so what happens, your current start increases. So torque and this relationship is, so your in this, like, TA proportional to IA square, okay, in a square way it is going to produce. As the load increases, armature current also increases, and torque increases proportional to the square of the armature current. Therefore, so it is means it is reaches to a certain limit, okay. So as the entire IA passes through, that's what its graph will be like this, okay. As this graph indicates, parabolic in nature, since TA is proportional to IA square, okay. So what happens here is when current start increasing, so your torque also increases square of the current, therefore it will be parabolic in nature, okay. After certain point, after certain time, okay, there is a limit. After certain time, what happens is this current start taking a sharp, means a constant direction, okay. It remains constant, like, it increases gradually, but it remains constant. Why it is so? As the entire current passes, okay, as entire current IA passes through the series field, there is a property of an electromagnet called saturation that occurs here, okay. What do you mean by this is saturation? Then this is, though the current through the winding increases, the flux produced remains constant, okay. After certain time, after reaching a saturation, even though current increases in the system, the flux remains, so whatever it is going to produce, the flux will be remains constant. Hence, after saturation, the characteristics takes a shape of straight line here, okay, you can observe, okay. As flux becomes constant, this we have shown here, right. And this one is the difference between TA and TSH, okay, this you can observe, right. So this is the difference between TA and TSH is called as loss torque, okay. So that is indicated here, okay. This is the first two characteristics of a DC series motor. We have two more, we'll see that. So this is what we have explained now, okay. See, let's see once again. As the entire current IA passes through the series field, there is a property of an electromagnet called a saturation, okay, that occur here. Saturation means though the current through the winding increases, the flux produced remains constant. Once the flux remains constant, so the saturation of a characteristic takes a straight line, okay. And the difference between TA and TSH is a torque, a loss torque, okay, that is also indicated in that. So second one is speed armature current characteristics of a DC shunt motor, okay. As you know, in a DC shunt motor, what is the speed and armature current characteristics? You just see once, okay. So this is the formula of the speed in series motor, okay. So we'll take that same formula, which is N is proportional to EB by phi. As we know this, what is the EB? We have to substitute. EB is, we'll write EB is V minus IARA minus IARSE, okay. This is the formula. As we know, okay, one more thing also we know, phi is proportional to IA, okay. Phi is also proportional to IA. So this EB formula we have to substitute in this equation, okay, divided by IA we have to write, okay. This is very important, else you can copy from the beginning what we have given the formula for this, okay. Once you have taken this formula, so even though load, when you load increases the load, so what happens, load current is also start increasing, okay. And then what we can say is when IA is start increasing, Okay, IA start increasing, voltage drop across this also start increases, and even this is also IA RAC, so this also start increases. This is V minus, this combination is going to reduce voltage. Okay, that means this difference will be less. Okay, so your back EMF is also less, meaning this is, okay, the meaning of this one is what, how we can take is, so now IA is, now IA is also in the denominator. Okay, in the place of 5 we can substitute the IA. All right, we'll take neatly, it is n is proportional to V minus IARA minus IARSE divided by 5 should be taken. Okay, actually it is n is proportional to EB divided by 5. EB equation is this one for a series motor. 5 is IA, right? Even though this voltage and this voltage start increasing when IA start increases. Okay, and then V minus IA is also start decreasing combination. So what we can say is, so due to this RA and RAC has a very small value, okay, very small value, and this is going to compensate your any, however IA goes on changes. Okay, then this voltage drops remains same. Okay, means like, lesser values. Therefore this difference of V minus this combination or this product is very less. So then what we can say is, so other words, V minus this combination is very less, we said. Therefore the change in V will be nothing but your EB, we can V only we can say. Okay, it remains same only we can say. Therefore what we can write is EB is approximately equal to V. We can assume that. Okay, EB is approximately equal to V, we can assume. Okay, I hope it is clear. Means numerator value V minus this combination, so difference between these two is a very less. Okay, V minus this combination is very less. Therefore what we can do is, this change, whatever this drop occurs, this is due to RA value and RAC value. These two values are very less. Okay, therefore what we can do is, we can assume, or we can say that constant means, assume that this voltage remains same. This is nothing but your EB only. Okay, back EMF and supplied voltages are same, we can assume. Okay, once you have assumed these two, so then what happens when you assume these two, so you can say it is a constant. When you say it is a constant, as we know, N is proportional to EB by IA. Okay, so EB is a constant term, then what happens, N is 1 by IA. Therefore speed and armature current inversely proportional. Therefore as the current increases, your speed goes on decreases. This is the one important factor for us to discuss in as a one topic. Okay, remember this, we'll be discussing this later. Okay, so remember, that's what this machine is not going to operate without a load. Okay, that is at the beginning. Okay, at the beginning current, if at all a current is current, as the speed increases, your armature current start decreases. Okay, so we'll see later. Okay, this is about a speed versus armature current characteristics. Last one is speed torque characteristics. Okay, speed torque characteristics, we'll see this speed torque characteristics. So as we have seen, T is proportional to IA square. Okay, this is for your torque and armature current in the first characteristics. And second characteristic, we have said N is proportional to 1 by IA. This is your second characteristics. By these two, what we can say is, observe, okay, in the place of IA, you see, I can write IA is proportional to what, 1 by N, right? You can substitute this IA here. Then what, T is proportional to 1 by N square. Okay, 1 by N square. correct? So if you'd like to speak in other words, then what we can write, speed is proportional to 1 by, take a square root on both sides, then it is the square root of t. I hope you have got this right. Okay, so as we know from first characteristics, t is proportional to ia square. Second characteristics, n is proportional to 1 by ia. Okay, in this equation, ia, I'll take this side, ia is proportional to 1 by n also we can say, right? Substitute this equation in this, then t is proportional to 1 by n whole square. In other words, if you would like to write it, is n is proportional to n, you send this side, and t take this side, means like this. If you like to take n, then it is n square is proportional to 1 by t. Then when n, if you say, it is 1 by square root of t. Okay, so therefore n is proportional to 1 by square root of t. Okay, inversely proportional, right? So thus the torque increasing when load increases, the speed decreases. Okay, the torque increases when you put a load. Okay, when you put a load on the motor, so what happens is torque increases, the speed goes on decreases. Okay, and then when on no load, okay, when on no load, right, torque is very less. Okay, torque is very less. And then what about this formula? N is, and hence the speed of the machine will be increases to very dangerous value, means very dangerously it is going to increase its speed. Okay, right. So thus the nature of the speed torque characteristics is similar to the nature of the speed armature current characteristics, that is this one. When the torque increases, the speed of this is goes on decreases, right? This is your characteristics of DC motor. And now we'll see one topic, as I said you in the previous one, third characteristics of a DC series motor. So based on that, series motor is never started and no load. Means if you'd like to start with your DC series motor, you should put a load on that. Without a load, it is very dangerous speed. Okay, why it is so, we have already discussed. Once again we'll recollect it. Motor armature current is decided by the load, as we know, right? And as we have observed, right, motor armature current is decided by the load, means both are directly proportional. Okay, when load increases, armature current increases. In case of DC series motor, okay, in case of DC series motor, phi is proportional to ia. This also we know. On no load, as ia is, okay, ia is the ia is very small. Okay, ia is a small, right? And hence what happens here, flux produced is also small, since these two are proportional. And when there is no load, then there is no current, means much current, right? So then what happens is flux will be lesser than, okay, less. Once you switch on the supply, what happens is there, since you have not put a load, a very small current will be flowing through that. Then since these two are proportional, directly proportional, flux will be very small. According to the speed equation, n is inversely proportional to 1 by phi. Then what happens is eb is almost constant, that we have assumed. Okay, so on very less or very less load, or a very light load, or you can say no load, okay, so what happens here is speed will be very high. The motor tries to run at a dangerously high speed, which may damage our motor mechanically. Okay, so this is about your characteristics of a DC motor. DC motor. Let's see the applications of DC motor. We'll see first based on this applications of this. First one, let's consider DC shunt motor. So since speed is almost all constant and medium starting torque, this will be used in blowers and fans, lathe machines, machine tools and drilling machines, and in milling machines. DC series motors has a high starting torque. Okay, so based on this, we'll be using in cranes, elevators, trolleys, conveyors, electric locomotives. And then cumulative compound motors are used in punches, rolling mills, shears, elevators, and heavy planers. A differential compound motor is used since it has a speed increases as the load increases. Will be not using in any other applications, but we are using in laboratories for a demonstration purposes. Okay, thank you.